Okay, let's get started. So last time I thought today was the day we talked about VinSim, but I forgot we have one more spreadsheet dynamical systems example, and that's what we're going to be talking about today. So trying to get used to this idea of breaking systems up into these tiny little discretized bank accounts that evolve over these tiny little compounding periods and show how that can allow us to simulate really anything that changes over time. So let's make sure, there we go. All right, so from last time, we started modeling these bacterial population dynamics, imagine clonal bacteria. And we basically talked about them being these kind of bank accounts where we talked about where imagine if the dollar bill was in a bank account and in the bank account, you get a little bit of interest each year. You don't get access to that interest until the next year, and you get a fractional dollar bill out the next year. But you have to wait the whole next year to get the interest. And that is how the bank account works. And so if we think about the bank account over time, we can start with some initial balance. We can figure out what the interest will be that year, and that tells us what the balance will be at the beginning of the next year, which then allows us to calculate the balance plus interest for the next year, which then allows us to go to the next year, and so on and so forth. And so this allows us to figure out how much is going to be in the bank account year after year without that compound interest formula. So it is a way of sort of saying we know how interest works from year to year, rather than figuring out a formula that allows us to see how it looks like over any time period. Then we can just start from year to year, and then we simulate year to year to year to year. And that's how that simulation works. And we say, well, if we know how to do that with a bank account, then how can we model a clonal dynamics in bacteria as if it were a bank account? And if we could somehow come up with a bank account model of bacteria, then we can simulate bacteria in exactly the same way, using all of the tools that we already know how to simulate compound interest. And if we use the bacteria example as kind of a toy case, then we can sort of generalize and talk about calculus more broadly. If we have rates of change of any variable, then we should be able to code them up in a spreadsheet and be able to solve any differential equation for us. So if you have dx dt equals 5 times x, you'll be able to put the 5 times x at the top of your spreadsheet, drag down, and then the curve that you come out will be that x that you would normally have to solve for in kind of a calculus class. So our bacteria, though, aren't like the bank. So we have to say, well, in our bacteria, you got one bacteria, and instead of after a constant time, it's after some random time, which we know is on average every, say, W time units, one bacteria becomes exactly 2. So that's something we have to deal with. In the bank account, after a known exact time, after a year, $1 becomes $1 plus a fraction. Here, after some unknown amount, after some potentially long period of time, 1 becomes exactly 2. So that it's somewhat similar, but it's clearly an important difference. And so 1 becomes 2, and then at some time less than W after that, one of those bacteria becomes another 2. At some time maybe less than W after that, another one of those bacteria becomes another 2. Maybe it's some time more than W. So under real situations, we get these random kind of trajectories where in real life, you're getting these doubling events that if you were to put a spacing in between every doubling event, it would be sometimes more than W, sometimes less than W. But on average, it would happen every W time units. And so we're going to take that average perspective and we're going to say, okay, what's the average population do? And so we're saying on average, every W time limits, 1 becomes 2. So if we imagine that that isn't happening spontaneously at these reproduction events, if we imagine instead that at every unit, at every tiny, tiny, tiny time unit, the bacteria are partially reproducing, then we can say, well, at what rate do they have to partially reproduce in order to occasionally match the real dynamics? And so what we're saying is that at very, very small time at very, very small intervals, we're pretending like the bacteria are oozing out partial bacteria at a rate at an instantaneous rate, a rate of just at that tiny little time interval of 1 divided by W, where you can think of the units of this as 1 bacteria divided by W time units. And so that gives me how many bacteria per second are being poured out of this bacteria into the new population that will be accessible in the next tiny little time unit. And so that way, so even though I'm focusing tiny, after one full after 1 full W time units, I will get a full new bacteria. But I'm not going to simulate every time step to be a whole W time units. I'm going to simulate a very, very small amount of that interval, which we'll call DT, which has to be smaller than W, much smaller than W. And then I ask in that small time unit, so if every bacteria doubles in an hour, then I'd say how much fractional bacteria is created every second. And so every second, I assume that there's fractional bacteria that itself isn't reproducing, that will start reproducing in the next second. During that second, I say every bacteria produces DT over W fractional bacteria. So if I multiply my number of bacteria by DT over W, it tells me in every second how much fractional bacteria will be added to the population in the next second for me to start this process all over again. And it turns this into kind of a little bank account. And so now we can think of that as that kind of bank account where we've got our initial investment here, which we're going to call a stock. And then we've got this fractional bacteria that's generated in this tiny time unit DT. And that together generates this kind of interest. And we refer to the rate of generation as a flow. Now notice that the actual interest is the flow times the tiny time interval DT. So the interest isn't the flow, the amount added isn't the flow, the instantaneous rate of it being added is the flow. Then we multiply that by the length of these DTs, and then that tells us how much bacteria we're going to add to our balance, our stock, in the next time interval. So every one of these intervals, just like a bank account, we start with a certain amount in the stock and we generate a certain amount of interest. But that interest is this flow rate, which is really where we're modeling the real dynamics, is coming up with the formulas for the flows. And then the computer generates the interest for us so that we can keep iterating. So then we get the stock plus the interest, and that generates our new stock for the next DT time unit. Each one of those has a flow. Each one of those flows gets multiplied by a little DT to figure out the interest added in the next time period. And this goes on and on and on. And so we can start with 1 bacteria, then we get 1 plus that 1 bacteria's interest accumulation, and then that new fractional bacteria's interest accumulation, and so on. And so that ends up giving us this trajectory over lots of periods of DT. And if our little time unit DT, where we assume there's no reproduction happening during that time unit, we kind of take all the reproduction that happened during that time unit and throw it into the next DT. If we make it really, really small, we will get a good approximation to continuous growth dynamics in bacteria. But if we make it really, really small, then we're gonna have lots of compounding periods. And so our spreadsheet is gonna go for thousands and thousands of rows before we even hit an hour. And so that's the reason why we can't just make DT arbitrarily small, because then we may run out of rows of the spreadsheet, or you'll actually start noticing that every time you load your spreadsheet, it takes longer and longer to load because it has to calculate these sorts of things. So ideally, we'd like to make this DT not super, super small, but small enough that this bank account approximation is close enough to the actual dynamics that occur in continuous time when these bacteria are just popping in, 1 goes to 2 in some W time units. So that's what we're trying to get here. And this is identical to arguments that you've probably seen the first time you took a calculus class when you started to come up with what the heck is a derivative. And when in that calculus class, you probably drew a curve saying that I have some variable f maybe, or in this case stock, And I know that F is, or stock is at this point at some time, and then some little bit of time later, it's at some other point. And so you can imagine that there is in reality, if we want to call it that, there in between these two times, the real stock might actually be curving up this way. And so it happens to intersect here and intersect here. And so in reality, our stock is growing like the red line, but we only simulate it at that point and simulate it at that point. Now, the derivative or the rate of change or the slope along this red line is constantly changing in between these 2 points. But our simulation just assumes that it's effectively constant that whole time, that it has the same slope here as it does up here. And if this interval is sufficiently small, then the small changes in the slope aren't going to be that different than just assuming that it was constant this whole time. So as long as we jump in time from a small unit of time here, from some unit of time to just a small unit of time later, and we assume a constant slope, not an increasing slope, then our approximation by taking this constant slope times this unit of time is going to give us approximately the right rise here. So this flow times dt that gets added every time period, this is our interest that's being added here. In reality, what's actually happening is bacteria could be created in between these points, and those bacteria are going to start to reproduce. So in reality, the reproduction rate of the bacteria probably increases between these 2 points. You got 5 bacteria and they're popping off new bacteria. And those new bacteria that are popping off new bacteria. And those new bacteria are popping off new bacteria. So in reality, the reproduction rate is increasing. But we assume we're zooming in on the system so far that there's going to be very little reproduction that's going to happen in between these 2 time points. So we might miss 1 or 2, but most of the time the population is not going to be reproducing much faster here than it is there. And that's what allows us to make this approximation where we're just going to say, how many bacteria do we have here? Assume only those bacteria are reproducing. That tells us how many bacteria we have over there. And that then gives us this rise. If we make dt too large, we're going to miss the creation of bacteria where I'm standing. And those bacteria are going to start reproducing. And we're going to undercount how many bacteria actually will be over here. So that's how we're simplifying the system. We zoom in on the system at a small interval where we can assume that nothing happens where I'm standing. So we only have to worry about what the system looked like there and what the system looked like there. If we make dt too small, we'll get a great looking system, but we'll have to make lots and lots of tiny little steps, which is wasteful. If we make dt too large, we're going to miss stuff that happens here. So our goal when you go into Vensim or Excel is to find that right balance of the dt so that your trajectories, your behavior over time settle down, so that if you made dt any smaller, it doesn't really change the behavior over time. And so you just stop making it smaller because it's more efficient to keep it at that kind of intermediate level. And we'll see an example of that in a second. But this is identical to when you learned calculus about saying that the derivative at a point is an approximation of the slope between 2 points as those 2 points get closer and closer and closer together. That's all we're doing. Okay, so the idea here, again, this is what's happening in reality, where we take this average behavior and we turn the average into a flow rate. And then from that flow rate, then we can come up with an inflow to our stock. Now, what we did in part 2 of your homework that's due on Sunday is said, well, what about death? Let's try to model the outflow rate. So this is a contribution. This is a derivative. This is how much the rate of change of bacteria is changing due to births. And it's 1 over W. So 1 bacteria per W unit time. Now you can say, well, bacteria also die. Well, in that case, 1 bacteria is sitting around on average every 3 time units and then disappears. So there's an outflow where every bacteria contributes to the outflow 1 bacteria per 3 units of time. And so just like the inflow, we took that multiplied by the number of bacteria times dt. For the outflow, it's this multiplied by the number of bacteria times dt. And that's what's going to give us this net flow calculation, which is the number of bacteria times the net flow, which is the inflow minus the outflow. So the thing in parentheses here, well, actually this whole thing, this thing in parentheses times bacteria, that is like the d bacteria dt. So I could say that this total flow, this net flow, this is like d bacteria divided by, or not divided by, this is like d bacteria dt, or d stock dt. Where I could say bacteria here, I'm calling is b. So this is a mathematical model that we can now simulate in Excel, where we're saying, we're like writing an equation where we're saying dB dt, the change in bacteria over time, is equal to the births minus the deaths per bacteria times the number of bacteria. And this here that you would have written out, that maybe using methods from SOS 211, you might be able to solve this thing and get a little exponential equation where this is in the exponent. We don't have to solve it anymore. We just put in this into Excel and then drag down and then plot that thing. And what you plot will be the solution to this equation. That's what we're doing when we're doing this in Excel. And so what do those formulas look like? You know, getting more and more concrete is that you're going to have an inflow, which is the number of bacteria in one row times 1 over W. You'll have an outflow, which is the number of bacteria in that row times 1 over 3. So then the flow for that row will be the inflows minus the outflows times the number of bacteria. And then that number of bacteria actually added to the next row will be this flow times dt. And that's what's going on in your spreadsheet to generate that curve. So let's see what that looks like. So I made this a little more interesting than the example I gave before. And by the way, if you haven't, I'm basically walking through the solutions to the assignment D1. So assignment D1 is due Sunday. By the end of it, so I gave you guys a chance to suffer through it on your own Tuesday. And if you haven't caught on now, I'm basically giving you the solutions ahead of when it's due. So by the end of these next couple of slides, you're going to know the solutions to assignment D1. All right, so this is the way I wrote it. As I said, I put my DT up here. I put my W, which is the waiting time until next reproduction here, and my average lifetime here. Now, these 1 over calculations, rather than putting them into the flows, I decided that I'm going to turn them into rates, and I'm going to do that separately so I don't have to have a lot of dividing in all of my expressions that I put in the spreadsheet. So this I didn't do last time, but I'm creating another set of rows, another set of parameters here that just take the W and do 1 over W to create a birth rate. And that's my inflow. And then I also then do the same thing with death rate, where I take my L and then I do a 1 over L. And so you can see that the W, 1 over 0.75, gives me 1.333, 1 over 3 gives me 0.33333. And it's just, I'm just making it, I'm just creating a converter which converts the average length of time between events into the average rate of production of events. It's just converting one unit to another. So does this step so far make sense? What I mean by going from time to rate, I'm just going 1 over, where you can think of the 1 over as one bacteria is coming into existence every W time units. That's where this 1 over. Or one bacteria is going out of existence every 3 time units, and that's this one right here. Okay. Questions online? Yes.
Like that's right on there. This one by yeah. So with Outflow, you just do like the number of bacteria times 1/3. Like that's the same thing or that's different.
That's the same thing, yes. So you could manually, in every one of your outflows, type whatever the cell for number of bacteria is times 1 divided by 3. The downside of that is if I said, okay, what if the bacteria now live for 8 time units? Well, then you got to go through and edit all of your equations. Whereas here, I could just edit it one place and then it'll trickle down through the rest of the spreadsheet.
But it wouldn't be like, it's not already pulled it all out.
No.
You wanna change it.
No. I'm just showing you how I parameterize these things. Of course, the more you break things out, the easier Eric will have to figure out what the heck's going on. But Eric is a very bright grader, and he'll figure those things out. So that is an acceptable variation. Yeah. Okay, so I got these rates now, and so then, so you kind of, this is sort of leading this forward. How do I then simulate the behavior over time? Well, time by convention always starts at 0. So I have a time column. My next time column is just the previous time column plus the DT. Remember the dollar signs? The dollar sign is particularly important, the second dollar sign in front of the number. That way, when you fill down, this DT stays, that it doesn't try to choose a new row. It always stays that one there. The first dollar sign is just there in case you wanted to fill right, but you're not going to fill right. But you'll fill down, and that's why that's there. So then that gives us our 0.01, because I'm on my DT 0.01. I then choose, and this is important, stocks have initial conditions. So I have to choose how many I start with. And in this case, I'm going to start with 1 bacteria. That's my initial condition on my stock. And then I need a flow for an inflow. So the inflow is just the number of bacteria, which is B9, times the per bacteria rate contribution to the inflow. And so every bacteria has an instantaneous rate. So this doesn't have the DT in it. DT does not come into play in the flow column. DT will come into play down here. DT is sort of hidden on purpose. So up here, this is the instantaneous rate. So at any instant, how many new bacteria are being created by all the existing bacteria. And it's the number of existing bacteria times the per bacteria instantaneous rate. Their birth rate, again, remember, is effectively 1 over W, but I simplified it to call it just birth rate so that I don't have to have a 1 over W. And then under deaths, similar idea. What's the per bacteria contribution to the outflow? No DT here. It's just the number of bacteria times, this is effectively 1 divided by L, or 1/3. But I just spread it out here to make it easier to see. And like if I would just put 1/3 there, somebody might not know what's going on. But now I see, what's B6? And I go to B6, I say, oh, it's the death rate. I see what they're doing. But they say, wait, I don't know what death rate is. What's death rate? Well, then I could look at this formula and it would say 1 over L. And I'd see, oh, I see, the death rate is just 1 divided by the average lifetime. That makes sense. So that's why it's nice to have these converters to spread things out. It makes it easier for someone to read. And then then the last important formula before I can fill down, in this formula will be the same for every single model that has 2 flows, an inflow and an outflow. This formula will be the same, whether it's bacteria, whether it's, it could be not even a population example, it could be whatever. Any dynamical system model you have, where you have 1 stock and an inflow and an outflow, will always have this thing here in the spreadsheet. And it's just the previous amount of that stock plus DT with the dollar signs times the net flow. And the net flow are all the inflows summed up minus all the outflows. In this case, there's 1 inflow, there's 1 outflow. And that's all I need to simulate this bacterial system with both births and deaths. And so I can fill that thing down. And so then I get all my times spaced by 0.01. I get my bacteria that's growing. And then I've got my flow rates. So I can see my flow rates are growing as well as the deaths here. And that's because if I look, my birth rate is bigger than my death rate. So that means even though there's an outflow that's pulling bacteria out, the inflow is greater than that. So the net flow is still going to allow for growth. If I were to go into here, and if I were to make that death rate like 5, so it's bigger than the birth rate, and I would make it 5 by making the length of life like whatever, 0.2, hopefully I did that right, then in that case, then this would decline to extinction. Yeah.
0.1.
I think I did make a 0.1 on Tuesday.
And so I based my model on second part on the 0.1.
That's fine.
Okay.
Yep. Yep. I think I asked you to use 0.1 in the assignment too. I don't think I asked you to use other DTs until part 3. All right, so any questions on the, I have a question online. Is birth rate the same as flow of new bacteria? Almost. Birth rate is like the individual bacteria contribution to flow. The total flow, remember, the bacteria stock is representing the total number of bacteria, and the flow is relative to the total number of bacteria. So every individual contributes 1.3 new bacteria per unit time. And then to figure out the flow contribution to the whole population, it's the birth rate times the number of bacteria. So that's why when we go back to the flow calculations, so if I go back to here, that's why this formula right here, that's the flow. It's B9, the number of bacteria, times the individual contribution to flow, B5. So that together is the flow, the inflow. The total net flow of the bacteria, which really I could call the flow, is the net flow, is the inflow minus the outflow. That right there that gets multiplied by DT, that is the real flow for the bacteria. So this equation here, if I could, again, if I were thinking about this in terms of calculus, this is effectively saying D bacteria dt is equal to the number of current bacteria times the bacteria birth rate. So I'll say RB, the birth rate, minus the number of current bacteria times RD, the death rate. And that's effectively what we see right here, because this thing here is the number of bacteria times the birth rate, RB. And this right here is the number of bacteria times the death rate, RD. And then this flow here just subtracts that minus that. And that's what gives me this here. So this, if I was in a calculus class, I might be asked, I might be given, I'm not going to ask you this, but if I was in a calculus class, I might be given this formula up here. D capital B dt is equal to B times R B minus B times RD. I might be given that. And then I would be asked, solve for B, capital B. And then that would produce a formula that would, so you could solve for that, and it would give you a formula B that would be a function of T, that would be an exponential growth curve. And that would equal some constant times the exponential growth curve to the some other constant times T. And so we can use calculus methods to solve for that. Or we do this, where we just put in the B that we put in, basically, this is the effectively right here, this C9 minus D9, that's me encoding that into the spreadsheet and then pulling the spreadsheet down. And instead of solving for that analytically, that ends up giving it. So this here is like plotting BT. This is B of T. And this here, not surprisingly, is an exponential growth curve where it's E alpha, some constant alpha to E to the some constant beta T. And if we're mathematicians, we could actually solve for what the alpha and beta are based on the growth rates that we put in here. but we're not worried about the analytical solution. We're worried about the graphical solution. And if we were to plot this analytical solution, we give us the exact same curve. But we don't have to do that because the spreadsheet did it for us. And so the curve that comes out of this is exactly what we would have gotten if we solved it with calculus, but we're not doing the calculus. We're just putting the derivatives in, pulling down, and having it graph the output for us. Okay, so any questions about that? Okay. All right, so then that brings up the question of how do you pick these DTs? Oh yeah, I'm sorry, go ahead.
Sorry, it kind of goes into where
Okay.
if we make the DT like substantially smaller, let's say like is your final result going to be a different number?
Yeah, that's exactly what we're about to go into here. Okay. Any other questions? Questions online? Okay. So yeah, then that's the thing. So this is the third part. Now, we're at the third part of that assignment that's due Sunday. And so in that third part, I ask you to compare the different DTs. And so you can do a DT of 0.01, 0.001, or 1. So in this case, I chose a really coarse grained DT. And you can see that it's coarse because it's kind of got these, I'm going to just point to them. There's these like corners here, like kinks. They're like kinks in the curve. And it makes sense that there's kinks in the curve because time is moving in steps of 1. And so we know there's 1 bacteria at time 0, and then it jumps to time 1, it jumps to time 2, it jumps to time 3. And that's the reason you get these like kinks where it's a straight line in between. All right, so if we look at these things, these all have the right shape. So they all look good in terms of shape. But if I look if I focus on the axis here, so let's see where these are all simulating for 5 seconds or 5 whatever time units. But if I look at the axis, then what I see is that after 5 time units at 0.01, I get something that's around, if I bring this back, let's say it's around, I don't know, 140. And if I do 5 seconds at 0.001, it's also about 140. So those two seem to agree. I'll put a check mark there between these two. But then notice when I do it for only a DT of 1, really coarse grain, then after 5 seconds, the bacteria growth is only like 30. It does not agree at all. So I'm undercounting my bacterial growth here. I have made my jumps so large that I've skipped important reproduction events. And so that bacteria is, I'm not accounting for all that new bacteria, and so it's not growing fast enough. So this is a bad approximation. But as I make my DT smaller and smaller, then I see that my curve kind of converges. You can see that this curve, if you look kind of, if you look at it, kind of is a little fuzzier than this curve. This looks smoother, and that's because you can see the steps really clearly over here. And here it's really hard to see the steps because it's really fine grained. But they both end at roughly the same point. So there's far less undercounting here than there is here. So if I'm only simulating for 5 time units, then this is a really fine, this DT of 0.01 seems perfectly reasonable. Now, if I were to try to simulate for 500 years, then this DT, if I really cared about my predictions way far out, then the undercounting would start to accumulate, and then this would be kind of a big problem. So they're always, it's always better to have a smaller DT, but for your particular application, you kind of want to pick a DT that's large enough for you to run lots of simulations, but small enough that it's accurate enough. And so you say, well, so like you could run this little pilot study, and here you could say, oh, for this pilot study, it seems like 0.01 is fine. So now I could go up and I could change my W and my L to different values. And as long as I don't change my W and L too much, then 0.01 is probably going to still be fine. And then I can very rapidly generate new outputs. Whereas if I would have gone to 0.001, then every time I change my W and an L, I might have to wait a long amount of time for my simulation to converge. So I could always use the smaller DT, but if I go too small, it's going to be a lot longer for me to play in the sandbox. It's like I want to be able to experiment, and the smaller I make my DT, the more costly my experiments are. All right, so the main takeaways here: find the right DT. Too large and your simulation is inaccurate. Too small and your simulation takes too long. All right, so any questions about that? That is pretty much all of that first assignment. So for Sunday, for that first assignment, I want you to just kind of reproduce the discussion that I just had here. Show me in your terms that you get what we just talked about there. Okay. Questions online? All right, so this is all moving toward being able to draw these things not in Excel, where it's cumbersome to come up with all the formulas and do the filling down and all that, but a much nicer platform for this, it's designed for this, like VinSim or Insight Maker. But it's the exact same stuff is going to hold. In VinSim, instead of coming up with a stock column, you're going to come up with a stock variable. So you're kind of going to build one of these boxed variables, that'll be your stock. And you'll end up putting into this stock, the only thing you ever worry about in a stock is an initial condition. So you'll put in the initial condition, an IC in here. And then the flow, that's where you put in the formula for your derivative, if you want to think in terms of math terms. And you'll end up plotting that in there. And then the converters, these are just for convenience. And this is just to sort of clean things up. So you'll be able to create these converters that that make the expressions you put in the flow simpler to look at. And so, and with all of this, you draw this thing out, the DT doesn't show up anywhere because your stakeholder does not care about the DT. Your stakeholder does care about what you've modeled mathematically, the structure, but you are the one responsible for choosing the right DT so that the computer approximation matches the real world. And so the stakeholder is going to count on you already picking a good DT. So in VinSim, there will be a separate menu where you choose your DT. You don't put the DT on the diagram, but it is there. It's just in a separate menu. In the spreadsheet, it shows up as if it's one of the key parameters. So your stakeholder can't avoid it in the spreadsheet unless you kind of hard code it into all your formulas. But it's the exact same stuff. And if I were to go and show from the very first slide here, slide 1, I gotta give a hint of this. So like a VinSim diagram for this system, you can see I've got the average time to reproduction. That is going to be W. I've got my average lifetime L. And you can see I can draw these converters out where my birth rate is just going to be 1 divided by that W. My death rate is just going to be 1 divided by that L. And I will then be able to take these death rates and birth rates and put them into a formula for births and deaths, those flows, which will just end up being the number of bacteria times that for that one, or the number of bacteria times that for that one. And then I go into VinSim, and I'll say the initial number of bacteria, the initial condition, is equal to 1. And then I'll hit go, and VinSim will generate a plot. And you can also have it generate a bigger plot, but it'll generate a plot like the one you see inside the little box there, which is exactly what we expect. And it'll also generate plots for all the other things. So that's a constant, which is why you see a single blue line. That's also a constant blue line. Births are rising, so are deaths. So that's where we're going. So this is going to be a much cleaner way to write these things than the spreadsheet. But behind the scenes, it's doing exactly the same thing we're doing in the spreadsheet. Okay. So that's all the old stuff. So I'll go back and ask, before we go to the new stuff here. Oh, and in fact, so yeah, so I went to the first slide, but I could have just done it here. So this is exactly what I just said about that first slide. I just should have checked my next slide. So yeah, this is written out there. This is the way we did it in spreadsheet, but we're going to learn to do it this way in VinSim and Insight Maker. And regardless of which way we do it, we are equivalently creating a numerical approximation of the math down here. Okay. So any questions about that? Yeah.
I have a question about you actually modeling things. So if you use two small DT and spreadsheet simulation, you can end up with many pages and slowing your sheet down. Will the same thing happen with Vixen?
So the question is, that if you buy my story, that if you make too small of a DT, you get too many rows, that'll slow the spreadsheet down. Does the same thing happen in VinSim? And yes, if you set your DT really, really small, you'll hit play in VinSim, and it'll actually take a very long time before it's ready to give you results. So it's exactly the same. And that's because behind the scenes, VinSim is building a spreadsheet and then running the spreadsheet. And so the and I'll actually show you when we do VinSim how to look at that spreadsheet after it's done building it, and even pull that spreadsheet back into Excel where you can do the graph. Any other questions? Yeah.
This is kind of going back to the part one on the assignment. Would you use the, so obviously time will be on this axis, but on that, will it be lower?
I would say definitely number of bacteria. If you want to also plot the flows, then you can. But I would say our stakeholder is going to be interested in how the bacteria are growing over time. They might be interested in how much the bacteria are reproducing, but normally for a growth problem, they're more interested in the population and not the population's derivatives. If you did plot them, the net, if you plot births minus deaths, then that would end up just being the derivative of this. And so you could confirm that if this thing's rising, that you'd also expect its derivatives rising. And so that would just be plotting the births minus the deaths, and that would also be rising. Yeah. Okay. So the tutorials that are already online, those are, because they're already made, they're pretty much always going to be an old sketch. But we're going to see that there's like almost no difference aside from the shape of the icons between the two. So the old tutorials that are online are all going to be an old sketch, but then examples, if we do live examples in class, I'll do them in new sketch. But if you have questions about the correspondence, they purposely made them similar enough. People were installing the old sketch and it didn't look enough like modern programs that it was sort of turning them off. And so they just wanted to dress them up, but all the same functionalities there. Okay. All right, well, let's keep moving then. So, so that was assignment D1. Assignment D2, which is kind of the complementary assignment. This is also due Sunday. It's a small assignment, and allows you, now that we know how to do D1, we're going to use what we learned in D1 to practice on a negative feedback example. So the bacterial growth example, there is negative feedback from the death, but the way the parameters are set up, the net flow is positive. So it's effectively a growth problem or a positive feedback problem. Now we're going to look at something that's fundamentally a negative feedback problem, and that's modeling a toilet flow as it refreshes. And so, so we're going to build a spreadsheet simulation where we start with a toilet that has initial conditions, and we're going to build an expression for how the valve pulls water in, because it pulls water in the most when it's empty, and then as it gets closer to the top of the tank, it stops pulling water in. So we have to model that, and then we're going to choose an initial water level. We're going to choose 0 because it's right after a flush, and then we're going to model what it looks like. Does the water rise this way and then level off, or does it rise this way and level off, or does it look like an S-shaped growth? We're going to see that. That's what we're sort of modeling here. So so you're going to build that in a spreadsheet. You're going to submit a causal loop diagram of the flow, and you're going to see an example of what that might look like. And then for extra credit on this assignment, if you so prefer, you can then complete the stock and flow diagram in the spreadsheet, but you're going to add a leak to it. And that's going to be a continuous leak, kind of like the continuous death rate in the bacteria case. So let's see what all that looks like. So this is the basic causal loop diagram for any balancing loop we have, including a toilet case. And like, in fact, this water level case I had before is effectively the toilet filling case, where this is the top of the tank, this is the bottom of the tank, and the eye is the valve deciding when to turn off the water when it hits the top of the tank. So, so if we were to swap in, so we can say here we've got a rate that is the flow, that's like the intake rate for the valve, and then our stock is the water level. So that's how we translate from water level and flow into the things that we'd see in the spreadsheet. So in our case, the formulas we have are the flow formula is just the target water level minus the current water level. So we're assuming that we could go to Home Depot or Lowe's or your favorite Ace or any hardware store, and you could buy a valve. So you can unscrew the valve that's currently in your toilet, screw it back in, the thing that's on the left side of the toilet. That valve has been engineered to, based on the way it's bent, based on the current water level in the tank, it chooses how much water to bring into the tank. And we're going to assume that it's been designed to bring in this amount of water, where if the tank is totally empty, it brings in, say, 15 centimeters per second. And that sounds like a lot, but it sounds like it's really fast. But as the water raises, this little auto leveling assembly here raises up and closes that valve off, so that when the water level is up to 15, the flow goes down to 0. So we have to just put this formula in our spreadsheet to simulate the action of this water control device, of this valve. And then what's the stock? Then it's just the water level, L. So we're going to put L in as our stock variable on that column. The flow column is going to have 15 minus the stock from that same row. And that's pretty much it. So if you were to imagine that there, this is our generic simulation spreadsheet. You're going to have a stock column, a single stock column, which you could call L, the water level. Its initial conditions are going to be 0 because it's after a flush, so there's no water in the tank. In the flow, it's just going to be 15 minus the water level. So I could write this stuff in. Again, I'm sort of filling this out for you here. Is that, so you imagine there's a single stock, which you could call L. Its initial condition is 0. There's a single flow, which is the inflow, which is basically the target water level minus the current water level. So in this case, I could say B3. And of course, since it's Excel, you put an equals in front of that. And this 15, if you really want to be good here, is instead of hard coding the 15 in the flow, you create a parameter up top here that's got the target water level. And that way you could change the target water level from 15 to 30 or whatever, and it would automatically change everywhere. And that's basically all you're implementing for this toilet is a single stock column and a flow column based on that. And then you're seeing what happens when you plot that thing. Does it look like the bacterial case, or does it look like something totally different? Question. Oh, great question. So the question was, where do I need dollar signs and where? So for this example, you wouldn't want dollar signs anywhere, because as you fill this thing down, you want that B3 to change to B4 to B5 and so on. But if I made 15 a parameter up top, let's say I put it in another, A4 or something like that, put it up here somewhere, I would need dollar signs there, because when I pull this down, I would want that cell to stay fixed. Okay. All right, so I've basically given you the formulas that you'll put the main formulas here, and then your goal here is then to create the spreadsheet using what you know. Like I said, the flow formulas, it's just the previous stock plus the flow times dt. So you do all that same stuff that we did with bacteria, but now we're doing it for the toilet. So all we change, the difference from the bacteria to the toilet, all we change is the flow. Everything else is the same. Okay. All right, so any questions about that? And this is pretty much the end of this. And so there's going to be plenty of time here at the end. If you want to work on this, we can work through it in class. We can also help people online. And if not, that's fine too. So So looking forward, again, this is lecture D2. Next week, we're going to start in Vincem and Insight Maker in D3 and D4. So there is a reading for Thursday, a week from today. That's the reading for D4. So the same suite of reading assignments as usual, the assessment, the exercise, and the perusal. Like I said before, start thinking about your final project teams, 3 to 4 people, modeling a dynamical systems problem. After the midterm, you'll have to, say a week after the midterm, you'll have to form your team. And about a week after that, you'll have to give me like a paragraph or so talking about what system you think you'd like to model. I'm not gonna, that system can change. I just need to show me evidence that you're thinking about it. Then if you don't like Vincem or you don't think you're gonna like Vincem, I encourage you to create a free Insight Maker account. Otherwise, it's fine if you just want to use Vincem. All examples I'll do in both Vincem and Insight Maker. And so the assignments that are due going into the weekend here, due Sunday, the muddiest point. You've got D1 from last lecture that now we all know the kind of solutions to. Today's D2, which is basically just a modification of D1. So these are kind of together meant to be kind of a part 1 and part 2 in a larger assignment, but you get kind of 30 points or whatever from both. And so it's sort of like a 60-point assignment, just kind of split up into 2. And then now we've got time to start this D2 if you'd like. If you'd rather just do it on your own, that's fine too. So then in other words, we talked about the midterm stuff. Any clarifications here? So we already talked about this on Tuesday. Just as a clarification for Thursday, what I'm going to do for stage 1 is I will open the availability window for stage 1 Thursday at midnight. I'll leave it open Friday and Saturday. So you can start, you get your 90 minutes. Once you start it, you got to finish it in 90 minutes, but you don't have to start it Thursday. You can start at any time Thursday, anytime Friday, anytime Saturday. So that means you can ask me questions all through Wednesday. Questions that I can answer are going to be extremely limited starting Thursday because I don't want to give away any hints about the stage 1 that might be out there. If you've heard about what's on stage 1 from somebody else, hopefully you won't be chatting about it too much, but so help me understand that. So I'll give you that 3 days. So maximal flexibility when you start it. You can come to class and work on it in class. It'll be, you'll still have to use the respondus in class, but I will be here and that way I can answer any questions you might have. And it looks like we can run the whole 90 minutes. And then over the weekend, nothing, but then Tuesday, what I'm gonna do is I'll open the availability window for stage 2, Monday, leave it open all day Monday, all day Tuesday, and all day Wednesday. And you'll have all of that time. You can go back to it, you can submit multiple times, or you can leave your one submission open and keep coming back to it. That will be open book, open notes, open collaboration with people currently enrolled in this class, not with people who have taken the class before or Chegg or any of the rest of those. And so, so that is a collaborative portion. And you can come to class Tuesday if you want to use this as a central place for you to work with people, or you can just totally skip that class that day, and that's totally fine too. And like I said, if you've done the little Respondus lockdown browser exercise, it's like a 1-question exercise, you'll get access to the midterm module, and there's a lot of resources there, practice midterms, previous midterms, and so on. So any questions about the timeline going forward, about the midterm, the stages, questions online as well? Okay. If not, then let's do the attendance exercise. And like I said, I'm happy to hang around until the end of regulation if you guys want to start on this assignment in class. So the question I'll give you is, what is the one thing you have to provide for every stock? Not flow, for every stock. So I was saying that that a flow is kind of related to a mathematical quantity that has a formula, and stocks don't have formulas corresponding to them, but they do have this one thing that for every stock, you have to provide this one thing in your spreadsheet. So think about that top row of your spreadsheet. What do you put in the top row of the spreadsheet for all the stocks? Not every other row, just the top row. And again, these are graded for just coherence, not correctness, for completion, not correctness. And that's all I got for you. So like I said, if you'd like to work on assignment D2, feel free to hang around here and ask questions. I can pop around. Otherwise, if you'd like to leave, that's fine too. Online, if you guys would like, I can put you into breakout rooms, or I can answer questions with all you in the big room. Just let me know how you'd like to proceed. And then let me just ask, any votes for breakout rooms online? Let me know, and I can put you into 2, 3-person groups. Otherwise, I'm happy to leave big room. What can I do for you?
So on problem 2, I didn't do, so I modeled deaths, flow of new bacteria, outflow of bacteria, and I did the same equation you did. I just didn't model, I guess, births and deaths. Is that okay?
What do you mean by you didn't, you mean you didn't put the rates?
Well,
I mean, you did, but they're in the formula.
yes.
That's fine. You don't have to break out the rates like I did.
Okay. And then for problem 3, again, same thing. I modeled it, took my screenshots of.
Well, I don't want you, well, it's probably better in your Word doc, just to like copy the graph, like right click on it and say copy, rather than taking screenshots. Like I don't want like any spreadsheet stuff to show up in your figures in your Word doc. Like I don't want to see rows of numbers in your Word doc.
Okay, let me get the Word doc. So so just go back and resubmit it, just delete all that, just copy the.
Yeah, because I mean, this isn't all that useful because you're gonna submit the spreadsheet separately. So imagine if I was a stakeholder, I really only care about the graphs. Now, so your grader is going to care about your code and the graphs. But imagine that the PDF or the doc is like for a stakeholder who really just wants you to do the graphs, and that's why it would be nice to like update the titles. And
Right, I
axes
didn't
and
do
things
any
like
of that. So update titles.
yeah, I would do titles and axes.
Okay, perfect. That answers my question.
Okay.
Appreciate it.
Yep. Let me make sure there's anything on one. Okay. Yep.
All right. I forgot to pay attention when they were talking about how Excel works. So,
No worries.
So for this guy,
And if you like to, you can set that. Well, I can't move that,
that
but
would be very useful. So how do I like apply that to the rest of the?
okay. Yeah. So one easy way to do it, if you mouse over the bottom right corner of a cell, see how it kind of, and then grab that corner and pull it down, and then let go. And yeah, so it shouldn't. So go back to. So see if you see the little green. See if you can try to grab just that kind of green corner.
Did I do it?
Well, the other thing we can do is if for some reason, usually I think there's a little square there. If you highlight the whole thing, like highlight, the next couple of, I'm sorry, highlight like that cell and then like the next 10 cells or something.
Wait, this one and the next one?
Yeah, so like you can hit like escape or whatever. No, hit escape to get out.
Oh my gosh, I'm.
No, that's all right. Just hit escape there. All right, now just hit like shift, hold down shift, and then click like 19, like click right down here. And then go up to, well, try right click because I don't see your edit menu. And then there's a fill. So it's been a while since I've done this on Windows, but we can see there's going to be a fill down, which normally there'd be like, where is fill in the Windows ribbon? Well, I think it's like Control D, so try that.
Man.
Oh, you know what it is? You've been doing it right the whole time. It's just you haven't filled in the rest of them out. So, no, you're fine. You're fine. It was my bad. So, highlight your births and deaths. So, we'll just to highlight both of those cells together. You have to like hit escape, and you can also use shift to do that. That's good. And then grab the corner, the bottom right corner. Yeah, let go of the. Okay, now grab the bottom right corner and pull that down. And then that's fine. We can just do that as an example. That's exactly what we want. That's good. And then do the same thing now for that 101. Just click on the 101, that cell, and then grab the bottom right corner and pull down, and then let go. And then scroll up. And now, this is actually working correctly. This is just telling us that maybe there's a problem in your formula. So let's look at your births and deaths. And under births, the problem is that B2 should be $B,
Oh
$2.
my gosh. And for this one as well, I'm assuming.
Yeah. And then do the same for deaths, right? Yeah, so you did that. And then so now your C and D, if you've done both the $B, $2s, then then highlight those two cells like we did originally, and then grab the bottom.
I don't know. I don't even know anymore.
That's fine, good there. And then grab those and drag them down. Or like I said before, you can highlight the whole area and hit Control D. That would have worked the same way too. And then now let's scroll up. And so those, and then, oh wait, and that's the other thing. So your formula here, go to your births formula. There shouldn't be just 1/, it should be B9 times that. So, or you could just do B9 divided by B2, that's fine. But you can just do B9 and then asterisks. And then, yeah, that's fine. And then the same thing for deaths. So right now you're simulating like, it's not changing with the number of bacteria, which is the reason why you're getting this funny result.
So then do the same thing.
Exactly, then fill it all down once more.
Okay, cool.
And there we go. So now you can see that this is growing. And so if you fill down your time, and you could grab any column and fill down, or sorry, any row of the time column and fill down. Same thing. And then you can now, if you were to plot the time column, column A, well, not all the column, but say all of these time, all these are number of bacteria, you'll start to see that exponential growth.
Okay, so for the assignment, we're doing this until like
5
5 seconds.
Right.
Okay.
So based on your DT, it might be 50 rows, it might be 500 rows, it might be 5,000 rows.
So this is going to be a little long.
Because it's 0.01, it'll be longer. The 0.1 will be shorter.
Okay, cool. All right. Understood.
Okay,
Thank you.
sure. And online, I'm going to mute my mic just so you guys don't have to hear me. Sure, no problem. If you have any questions, then just voice up and I'm happy to come back in. All right, so we are at past 4:15, so I'm going to go and end the meeting. So anyone online, if you have any other questions, this is sort of the last chance. Otherwise, you feel free to email me. Okay, in that case, I will see everybody next weekend.